Good day, everyone. Today's video discussion is about power. One thing that comes to my mind when we talk about power is this famous line coming from a movie. With great power comes great responsibility. Coming from Uncle Ben. Now, our common notion of power is something that we can relate with a supernatural ability. But it's also important that we have to reconsider our idea of power as a simple human capacity. Like for instance, when I was in high school, me and my friends are playing basketball. And at that time, I feel that I am powerful because when I raise my hands up to play defense, the offensive player, together with the rest of my teammates, are moving away from the ball. And so I snatch the ball and use that as an opportunity to make a game-winning shot. And the next day, I found out that none of my friends would want to play basketball with me again. Perhaps that was because of my power. Non-contact armpit power. Okay, just kidding. Now, what does science tell us about power? In a scientific perspective, power is defined as the rate at which work is done or energy is transferred over time. So there are two concepts that is embedded in the idea of power. One, it talks about how fast work is done in a certain period of time and how much energy is transferred in a particular unit of time. Now let's consider these formulas that describe power. Power is represented by a symbol P is equal to work, which is W divided by time. So work here is expressed in joule, while time is expressed in terms of seconds. And another formula that talks about power is the rate at which energy is transferred. So E represents energy and T is for time. So these equations give us a certain unit that describe power. And joule over second is equal to a unit called watts. However, don't get confused with W as a unit and W as a quantity. If you see a particular symbol W together with other symbols like P equals W over time, that means the W there is treated as work because it addresses a quantity. But if you see a letter W together with a number, that means it is regarded as a unit. So here, watts is a unit of power. Let's have this example. Mang Juan and Canor are in the weightlifting room. Juan lifts the 100 Newton barbell over his head 10 times in 1 minute, while Canor lifts the 100 Newton barbell over his head 10 times in 10 seconds. Question: which one performs the most work? And which one has more power? So first, we need to establish facts regarding Juan's and Mang Canor's description. So Juan was able to lift the barbell 100 Newton in 1 minute. that is repeated for 10 times. While Canor is able to lift a 100 Newton barbell in 10 seconds, also repeated for 10 times. Therefore, if you're asked which one is more powerful, and that would be Mang Canor. However, Juan and Canor is actually doing the same amount of work because they were able to lift the same barbell the same distance above their heads. Yet, Mang Canor is the most powerful since he does the same work in lesser time. That is why power and time are inversely proportional. Let's have another sample problem with regards to power. What is the power output of a baggage loader that pushes the box 5 meters in 3 seconds with a constant force of 12 Newton? First, let us identify what are the given in the problem. 1, 5 meters, so that's distance. Second, 3 seconds, so that talks about time. And you have force, which is equal to 12 Newton. So, we are asked to solve for the power output of the baggage loader. Mathematically, we can express power as work divided by time. And work done, in our previous video lesson, work is force divided by time. So, force is 12 Newton, distance is 5 meters. So 12 times 5, that gives us 60 joule. So 60 joule divided by time, which is 3 seconds. So that gives us an answer of 20 joule per second, or that the power output is 20 watts. Another sample problem. A basketball player with a mass of 80 kilograms jumping 0.6 meters in 0.5 seconds to slam the ball. How much is the power output of the player? So with this, we are given the mass, 80 kilograms. We are given the height or the distance above the ground, which is 0.6 meters. And time is in 5 seconds. And we're asked to compute the power output of the player. So here, first, we need to consider work done in this scenario. So work can be achieved when we multiply, this time when we multiply mass times g. So the g here is the acceleration due to gravity, since the player is jumping off the ground. So when we multiply mass and acceleration due to gravity, what we get is the force. And then once we have the force, we multiply it with distance or height. So force times distance, we get work. So in our solution, we have there work is equal to mass times the acceleration due to gravity and the height. So the mass of the player is 80 kilograms, while the acceleration due to gravity is constant. That is equal to 9.8 meter per second squared. But in our classroom or in our lesson, we are using 10 as the value of g. So you may replace this with 10, or you may keep it as 9.8. It's up to you. And then the height is 0.6 meters. So multiplying these three, you will get a product of 470 joule. And 470 joule is the work done by the player. And how do we get the player's power output? Is simply divide the work by time. And the time it took to complete this work is 0.5 seconds. Therefore, power is equal to 470 joule divided by 0.5 seconds. And our answer is 940 watts. Okay, so here are some of the context, some of other contexts of power. So it's called mechanical power when it is generated from moving objects, like in machines. So there, we can compute the power using the formula for power is equals to force times distance divided by time. So take note that this distance divided by time is a formula for speed. And you can make use of which and substitute it with a value or with a quantity of speed. Therefore, the formula can also be expressed as power is equals to force times speed or velocity. Okay, so that's for mechanical power. I will not introduce sample problems on this because I am just sharing to you what are the other contexts of power. So in this regard, it's mechanical power. Second, for electrical power. So this is power in electric circuits. So the formula for the electrical power is equal to I times the V. So I here represent current, while V is for voltage. So getting the product of current and voltage, you will end up with a unit of power. So power, the unit of which can be expressed in watts. It can also be expressed in kilowatts, like in this case for electrical consumption. Now, here are some of the other real-life examples of power. So, in a department store, when you see a light bulb and the description says 100 watts light bulb, it means it uses 100 joules of energy per second. That is equivalent to 100 watts light bulb. So, it transfers 100 joules of energy per second towards its environment. Another, a Toyota Vios is powered by a gasoline engine that produces 106 horsepower. So HP here means horsepower, while a Ferrari may produce up to 800 horsepower. And the conversion tells us that 1 horsepower is equal to 746 watts. So if you are curious about how much power generated by a Ferrari, you can convert 800 horsepower to an amount of watts. Okay, so here that is 800 horsepower is equal to 596,800 watts. Another, in sports, a professional boxer delivering a powerful punch can generate around 700 to 1,000 watts of power for a brief moment. And this time, we are now moving towards the activity part of today's video discussion. That's all for this session. Thank you so much for listening. And remember, keep going, keep growing. King Juan Learnings. Embrace learning.